Hello everyone, welcome to my channel The Online Educator, and we'll be recontinuing the lectures of the haloalkanes and haloarenes. Today we'll be discussing the reactions of haloarenes. We have three types of reactions: the nucleophilic substitution reaction, elimination reaction, and the reaction with metals. So first we'll be discussing the nucleophilic substitution reaction. So now we come to the neutrophilic substitution. Aryl halides are extremely less reactive towards nucleophilic substitution reaction. So here we will be seeing that the haloalkanes were reactive in the neutrophilic substitution reaction, and in the haloarenes it is extremely less reactive. Alright, it has four different reasons. The first reason says is the resonance effect. The second is the difference in the hybridization of carbon atom in CX bond and the instability of the phenyl cation, and the fourth reason is, I'll say you. So here is the four reasons. So if we discuss the first reason, which is the resonance effect. In haloarenes, the electron pairs on halogen atoms are in conjugation with the pi electron, okay, of the ring. So here they give a resonance. So here the electron revolve in the benzene. Alright, and here we see the resonating structures. This electron, the double bond, it jumps on the electron, and here we see the resonating structures, and through resonance this becomes stable. Alright, so CCl bond acquires a partial double bond character due to resonance. Alright, as a result the bond cleavage in haloarenes is difficult than haloalkene, and so they are less reactive towards neutrophilic substitution reaction. Why? Because the CCl bond has a partial double bond character. Why partial double bond? Due to resonance. So the bond cleavage is difficult than the haloalkane. Alright, so we get our first reason for the resonance effect. The resonance effect says that the CCl bond acquires a partial double bond character due to resonance. As a result, the bond cleavage is difficult in haloarene. Alright, because here the CX bond will have a partial double bond character, and here it doesn't have such kind of thing. So it is difficult for the haloalkene. Okay, it is difficult for the so it is difficult for haloarene for the neutrophilic substitution reaction, so it is less reactive. Okay, now we come to the rest of the points: difference in hybridization and the rest of the points. So now we come to the second point: the difference in hybridization of carbon atom in the CX bond. In the haloalkene, the carbon atom attached to the halogen is sp3. Okay, and in the case of haloarenes, the carbon atoms attached is to sp2 hybridization. Look here, sp2. We know that the benzene, each benzene's carbon is having sp2 hybridization. Okay, and the haloalkene, it is having sp3 hybridization. Now if I compare the electronegativity comparison, so we know that more the s character present, more is the electronegativity. So in sp3 the electronegativity is 25%. In sp2 the electronegativity is 33.33%. I hope that 25 is less than 33, right? So the sp2 is more electronegative. So the bond of CX in haloarene is more electronegative than haloalkene. And one more point is that in the haloalkene the CCl bond is having 177 picometer, and the CCl, the CX bond length of the haloarene is 169 picometer. So it is difficult to break the shorter bond than the longer bond, because we know that the bond length is inversely proportional to 1 by bond strength. So more the bond length, less is the bond strength. It is easy to break. Less the bond length, more is the bond strength. It is tough to break. So the haloarenes S character is more, okay, so it is more electronegative than the haloalkane. Alright, and the bond length or the picometer, okay, so the CX bond length is less of haloarene, and it is not easy to break. So the haloarenes are less reactive as compared to the haloalkane in the neutrophilic substitution reaction. We take our third and fourth point now. So now we come to our third point, the instability of the phenyl cation. In haloarenes, the phenyl cation, it forms an ion. Okay. In case of haloarenes, the phenyl cation is formed as it is a self ionization. We know, and we are knowing from the result, that in haloarenes the phenyl forms itself ionized and it forms phenyl cation. And we know in Sn1 mechanism, in Sn1 reaction, we saw that first the carbo 3 degree or the carbocation is formed. Alright, first the carbocation is formed, then the nucleophile comes and attack, and this carbocation is not stabilized by the resonance, will not be stabilized by resonance, and therefore S1 mechanism is ruled out. Okay, so the instability of the phenyl cation, this instability, the phenyl cation is not stabilized by resonance, and so the aryl halides are less reactive. One more, the last reason we have is the because of the possible repulsion, it is less likely for the electron rich nucleophile to approach the electron rich arene. We get a repulsion between them. Okay, the electron rich nucleophile and the electron rich arene, so it is a possible repulsion, so it is less reactive in the nucleophilic reaction. I hope it was clear. The first reason said was the resonance effect. The second reason was the hybridization. All right, it had sp2, which had the more electronegativity. All right, the resonance effect had that the resonance effect make it stable, so that the nucleophile cannot attack on it. The third was the phenyl, the instability of the phenyl cation, and the fourth was the repulsion of, okay, the repulsion of the electron rich nucleophile and the electron rich arenes. Now we come to our next point, the elimination reaction, but I'll be discussing some reactions now of the nucleophilic substitution reaction. So now we see the replacement by the hydroxyl group. Okay, the chlorobenzene, it reacts and it gives us the benzol. Okay, the hydroxyl group comes and sticks over the benzene. Now this NaOH, the nucleophile created is OH minus. Okay, and then after that the second process is H plus. The presence of electron withdrawal group NO2 at ortho and para positions increases the reactivity of haloarenes. Okay, the presence of electron withdrawing group NO2 at ortho and para positions. All right, so we see that it reacts. Okay, the it reacts and it gives us the para and the ortho and the para products. Okay, right, NaOH with 443 Kelvin and the H plus again. Okay, and here we saw that the presence of electron withdrawing group, the ortho and the para positions, increases the reactivity of haloarenes. Okay, and when we have the electron withdrawing group in the meta position, we see there is no reaction, there is no reactivity in the haloarenes due to presence of the electron withdrawing group at meta position. So we got to know that in presence of electron withdrawing group of NO2 at ortho and para position increases the reactivity, but the meta position gives no reactivity. Okay, you see it's nothing changed, so it gives no reactivity. Okay, in the meta position, and here the Cl gets converted to the hydroxyl, the replacement. All right, replacement by hydroxyl group. So we got to know that the meta position gives no reactivity in the haloarenes, and the ortho and the para position increases the reactivity of haloarenes. In the next video we will be discussing, in the 5.4, we will be discussing the elimination reaction and the reaction with metals and the remaining reactions of the haloalkanes. Thanks for watching.